Good morning and welcome to Tech 293 on Tuesday, April 6th. I hope you enjoyed doing Lab 7 last week. That's one of my favorite labs, and I always enjoy doing that, so I hope you enjoyed it as well. Today, we're going to start a brand new topic in this class. It happens to be one of my favorite topics, and it leads to one of my favorite labs, which is Lab 8. And for the next 2 weeks, we're going to talk about beam bending. That is where you have some type of beam, and we'll talk about all these different variations of types of beams and how you support them and how you apply the load to it and things like that. But basically, you have some kind of a beam, you support it in some way, and then you apply a load to it in some way. And we're going to calculate how much does it deflect? How much is the deflection of the beam when you apply a load to it? So that's basically the topic for the next 2 weeks, including Lab 8. So let's take a look at the schedule real quick. First of all, note that the lab report for Lab 7 is due on April 8th. That's Thursday, April 8th, so don't forget about that. And you can see that we're going to spend the next 2 weeks talking about beam bending. We're going to divide it up into a couple of different class sessions because there's quite a bit of material to talk about. What I'll probably try to do is cover most of the theory today in today's videos, and then we'll do a bunch of example problems in Thursday's videos. And then if there's any material left over, then we'll cover that on the 13th in a video on the 13th, if necessary. But we'll just kind of see how it goes. We also are going to be doing Lab 8 during that time period. Normally, in most semesters, we would go as a whole class to the Woods lab, Turner 169, same place you did the Sharpie V-notch testing. And as a whole class, we would work in groups, but the whole class would be there at the same time. And each group would build a beam out of wood to test in Lab 8. However, I can't have the entire class in the same room at the same time this semester. So I have to divide it up, and we can't all be there at the same time in the same room. So what we're going to do, if you see on the schedule, half of the class is going to come in person on April 8th to the Woods Lab, Turner 169. And those groups are going to build their beams. So I'm thinking about groups 1, 2, and 3 will come to Turner 169 on April 8th at our normal class time, 2 p.m. And those groups will build their beam that they will then test in Lab 8. So groups 1, 2, and 3 will come to the class on April 8th in person. The other groups 4 and 5, will come to the Woods Lab, Turner 169 on April 13th to build their beam that we will then test on April 15th. So the entire class will come, not all at once, but in staggered time slots, will come to the Instron machine lab on April 15th, and we will test the beam that you built either on April 8th or on April 13th. All right. I'm going to give you a bunch of guidelines about the beams, so it's not just a complete free-for-all. There are some rules that you have to follow when you're building the beams regarding the design of the beams. So let's actually go ahead and look at that right now. It's in Lab 8, and Lab 8 starts on page 91. And in the middle of page 91, you can see all the guidelines and rules for your beam. So the rules for the beam that you design and build either this coming Thursday or next Tuesday. First of all, it has to be all wood and glue. You can't have any other components, no bolts or threaded fasteners or metal pieces or anything. Second of all, it has to be more than one board because it would be too easy just to let you come to the lab and cut down a 2x6 to the right size or something like that. So it has to be at least 2 boards glued together at a minimum. You can go crazy and you can do whatever arrangement you want, but it's got to be at least 2 boards cut down to the right size and then glued together. But it can be more complicated than that. The third one says it needs to be at least 19 inches long. That's because of the test fixture that we're going to test these on. We'll talk about how you can support beams in a little bit later section today. But the way we're going to test your beams in Lab 8 is it's going to be a simply supported test fixture. That means it's just going to be resting on the test fixture, kind of like this, where you got a support on the left, a support on the right, and then there's going to be a force from the Instron machine that comes down in the middle, right like that. So these supports are 18 inches across. The span of the beam in Lab 8 is going to be 18 inches. So you need to make sure that your beam is at least that long. I would recommend a little bit longer. That's why I say 19 inches. You can make it longer than that. You can make it 20, 21, 22 inches. That's fine. It's just not going to do any good. Having the extra beam length on the ends outside of the supports isn't really going to do any good, but you can. It just needs to be at least 19 inches long. The next bullet point says it can be up to 4 inches wide. That also has to do with the supports. Those supports that are going to support your beam are 4 inches wide. So your beam can be 4 inches wide so that it can rest on your beams. It can be up to 4 inches wide. It has to be at least 1.5 inches wide. And just for perspective, that's the width of a 2x4. Not that you have to use a 2x4 by any means, but it has to be at least 1.5 inches wide. That's so when we're testing your beam, it doesn't fall over. It doesn't tip over. Because if your beam tips over, then that kind of invalidates the test because that throws out the calculations that you already did or you will do on this beam. So you need to make sure your beam's at least 1.5 inches wide so that it doesn't tip over as we're doing the testing on it. So between 1.5 and 4 inches wide and at least 19 inches long. The second to last bullet point is actually for you to make it easier for you to do the calculations. I recommend that your beam is symmetrical top to bottom. So the top half and the bottom half of your beam are the same. They're mirror images of each other. If it's symmetrical about the central axis, and we're going to call that the neutral axis in a few minutes, but if it's symmetrical about the center axis of the beam, that will make your calculations that you have to do in Lab 8 a lot easier. It's possible to do calculations if your beam is asymmetric about the central axis. It just makes things more difficult to do some of the calculations. So it's not a rule. The second to last bullet point is more of a recommendation than a rule to make it easy for you. And the last bullet point there is one of the more important ones, the cross-sectional area. So if you took a slice of your beam, the cross-sectional area of your beam needs to be at least 2 inches squared and not more than 4 inches squared. And the reason I do that is to give you a window to make sure that when you test this, we're going to get some deflection. I mean, it would be relatively easy for you to take a whole bunch of, say, 2x12s and glue a bunch of 2x12s together and then subject it to a load. And guess what? It's not going to get much deflection if you glue a whole bunch of beams together. If I allowed you to have 20 or 30 square inches for your cross-sectional area, then you wouldn't get much deflection. But that kind of defeats the purpose of this lab. We're trying to learn how to calculate deflection in a beam. So I do want to make sure that the beam that you build is going to have some deflection so that the calculations actually mean something. So that's why I make you build a beam that fits within this window, at least 2 inches squared. Otherwise, it's going to be too floppy, and not more than 4 inches squared. Because like I said, if it was more than 4 inches squared, you would not get as much deflection of the beam when we test it. All right, so make sure you take a read through those bullet points on page 91. And what I would really recommend that you do, since when you come to the lab, the Woods lab, to build your beam, you're only going to have one class period to build your beam, about 2 hours to build your beam. So I would really recommend that you communicate with your group ahead of time, send some emails, or maybe set up a Zoom meeting or something. If you need help with that, let me know. I can set up a Zoom meeting for you if you want, and discuss your design plan ahead of time. That way, when you come into the lab, either on Thursday or next Tuesday, you don't spend half the time just talking about what the design of your beam is going to be. So you may as well make efficient use of the time that you're going to spend in the lab. And I would recommend that you do that by having some kind of a plan for what your beam is going to look like before you come into the lab. If you have any questions about the rules for your beam, let me know. I'll be happy to answer any questions. I also want to point out that there is some extra credit opportunities on this lab. So take a look at page 94, the last section of Lab 8. And there's actually 2 opportunities for extra credit. When we test all of your beams for Lab 8 on the Instron machine, I'm going to give some extra credit. First of all, to the team who most accurately predicts as a team. So you have to come to a consensus. And I'm going to ask you, before we test your beam, I'm going to ask you what your prediction is as a group. So you need to come to a consensus as a group. What is your prediction for how much load your beam is going to support before it fails? We're going to talk about some calculations that you can use to estimate that, so it doesn't have to be just a wild guess. It's probably better if that's more of an educated guess. And we're going to talk about how to make those estimates and calculations in the next couple of class sessions. But I don't really care at that point when I'm asking you what your prediction is. I don't really care how you came up with your prediction. It can be a wild guess if you want, but you need to tell me what your prediction is. And then after all the groups have done their testing, then we'll look at the difference between what each group estimated their load would be, their max load would be, and the amount their beam actually supported. Don't worry, there aren't any rules like you can't go over, like the Price is Right or something like that. No, where you can't exceed. No, I'm not going to do it like that. It's just going to be the absolute value difference between what you predicted and what your maximum load on your beam actually was. So the absolute value of the difference there. We'll compare that across all of the groups in Lab 8. And the one who was closest to the actual load their beam supported will get 3 points of extra credit. Everyone in their group will get 3 points of extra credit on this lab. The other extra credit is for the group that designs and builds the beam that is the strongest. So whichever beam is able to support the largest amount of load before it fails, that group will get 3 points. Everyone in that group will get 3 points of extra credit on Lab 8. There is a tiebreaker. I don't think this tiebreaker would be necessary. I've done this type of lab for a couple of years, and I have changed the rules a little bit slightly over time, so it's not always exactly identical, but I've never had a group that has maxed out the Instron machine. Never had a group that built a beam that could actually support 20,000 pounds force. But hey, there's always a first time for everything, so try to see if you can design and build a beam that can max out the force on the Instron machine. If by some kind of miracle there are 2 groups that are actually able to max out the Instron machine, however unlikely that is, then in that case the tiebreaker is whichever group whose beam deflected the least at 20,000 pounds force. But trust me, that won't become an issue. I've never had any group that built a beam that was able to support 20,000 pounds force. That's a lot of force considering these limitations I'm giving you, like it has to be between 2 and 4 square inches. It's pretty tough to build a beam out of wood that can support 20,000 pounds force when you're limited to 4 square inches. All right, so I think that kind of goes and provides an overview for the schedule and the lab that we're going to do as a result of this discussion. But let me know if you have any questions about the schedule or about Lab 8. So we're going to start talking about beam bending now. And today we're going to focus on the theory of beam bending, how it happens, and how do we predict how much beam bending is going to happen when we apply a load to some particular beam. So to get started in our discussion, I think it would be helpful to do a little virtual experiment. I'll do a little experiment while you watch. That's the best we can do right now. So I'm going to send it down to our special correspondent in the materials testing lab to do a little experiment for us. I'm down here in the classroom right next to the Instron machine to do a quick little demonstration about beam bending. And what I want to talk about are the things that affect the amount of bending we're going to get in a beam. Because a lot of these things are more intuitive than you might think. We'll talk more about them in a little bit, but we can demonstrate some of these pretty easily. So to do a little test here, let's say that I've got this piece of wood. So it's like a 1x2 made out of fir or pine or something like that, some soft wood. And let's say I've got it supported like this on this desk, and I want to apply a force right here in the middle. And I want to make this as strong as possible. I want this beam to support as much force right here as possible. Right now, it can't support much of anything, right? Maybe like a couple grams or something, you know, not even a kilogram right here. So what are some things that we could do to this beam to make it stronger? You can probably come up with quite a few on your own right now. So some of the things that I can think of right off the top of my head. What if I clamped this down? I don't have a clamp on me right here, but maybe I can put my body weight on it to simulate that. Now it's quite a bit stronger, right? It's quite a bit stronger. However, there's still some flex. I hope you can see that. Even though the beam is clamped here with my body weight, there's still some flex in this beam. So, you know, it's a lot stronger than it was, but still not really strong. What are some other things I could do? Well, I could change the way this is supported. Right now, this is just sticking out from this desk. This is what we call a cantilever beam. That means it's supported on one side and it's got one side that's not supported. That's a cantilever. We'll talk about that more. What I could do is turn this into a simply supported beam by going like that. And now it's simply supported on both sides. It's just resting on both sides. And I could apply a force in the middle and it's quite a lot stronger now. I still would not want to put all my body weight on this. There's definitely a lot of flex in here, but it's a lot stronger than it was as a cantilever. Another thing I could do is I could clamp down these sides. If I had some clamps, I could clamp it down here and here. That one might not be quite as intuitive, but as it turns out, that does change the amount of force that I could apply in the middle. The beam becomes quite a bit stronger if I clamp these ends down. So it's not just resting here like a simply supported beam, but if I actually fix the sides of the beam, that actually makes it stronger. All right, so I could do that. What else could I do to change the amount of force this beam can support? Well, one thing I could do is I could change the orientation of this beam. The way I had it, it was laying down flat. But if you've ever played around with boards like this, you probably recognize that if I rotate it like this, it would be quite a bit stronger. So now it's on its flat horizontal edge, but if I rotate it up on its narrow edge, now it's quite a lot stronger. Now it probably can, yeah, it can, I'm on it right now. My feet are off the floor. So it actually can support all of my body weight. It's bending a fair amount when I do that, but it is supporting all of my body weight. So that made a pretty significant difference. We'll talk more about what that does and how to calculate it in a little bit. But what that does is change something called the moment of inertia of this beam. As I change it from this orientation to this orientation, that changes the moment of inertia of this beam. All right. As we're talking about dimensions, of course, I could change this out for a larger board, right? So that was a 1x2. Instead of a 1x2, I could use a 2x4. This is a pine 2x4. And of course, I could put it in the horizontal direction like this. And this is pretty strong because it's a 2x4. But I could make it even stronger if I put it up on its narrow edge. Now it barely even deflects when I put all of my body weight on it. All right. What are some other things that I could do? We talked about how we could clamp both ends. That would change the amount of force it could support. What if I change the material of the board? So instead of making this out of pine wood, maybe I make this out of aluminum or steel or some other type of metal. Of course, that would change the material properties of the beam, and that would allow it to support more force. And the last thing I want to point out right now is that the way I apply the load actually matters. So if I put all of my force in a small area right here, then that's one way of loading it. But if I were able to spread out my force along this whole beam, say I had some type of maybe another beam on top of that would allow me to spread out my force. If I were able to spread out the load more evenly along the beam, then that would change the amount of force that I could apply to the beam as well. So what are the things that we talked about just now that we said could affect the amount of force the beam can support? So in no particular order, we said that the changing from a cantilever to a simply supported to a fixed on both ends, clamping down on both ends, that would change it. That's the way that we support the beam. We said that changing the moment of inertia, which is the geometry of the beam, even the same beam going from horizontal to vertical, that changes the moment of inertia of the beam. So that's like the geometry of the beam. We said that changing the material itself, say from pine wood to oak, or from oak to aluminum, or aluminum to steel, that would change the bending properties of the beam. And the last thing we said was that the way we distribute the load on the beam, whether it's a point load applied right here, or if it's a distributed load, like a bookshelf, that's the best example of a distributed load. A bookshelf where the load is applied all along the length of the beam, that will change the amount of force that the beam can support. So those are the most important things when we talk about how much load the beam can support. And we'll talk about each one of those in a little bit more detail in just a minute. All right, most of those things were pretty intuitive, right? So keep those things in mind as we talk about beam bending in a bit more detail. Beam bending, in other words, flexural testing, is what we're going to talk about today. In a nutshell, this is the type of testing that we're going to do. In fact, this is exactly what we're going to do for Lab 8. This is an example of a simply supported beam, which we'll talk more about in a couple of minutes. You know it's simply supported because the beam is just resting on the supports on both sides. This is called the span of the beam, the distance in between the supports. And we're going to apply a load right in the middle of the beam. This is also called a 3-point bending test. 3 points because there's something applied to the beam at 3 points. Right here and right here are the supports, and right here is the force that is applied. Of course, as we apply this force, there's going to be deflection. The deflection of the beam is going to be this distance right here between the upper surface here where it's unbent and the upper surface here where you have a deflection. All right. As we're testing this, let me give you a preview of what we're going to talk about. Think about this beam as it's being bent. Think about whether this beam is in tension or compression. Is this beam right here in tension or is it in compression? Or is that kind of a trick question? We'll talk more about that in a little bit. The deflection that we're going to talk about, and eventually I'm going to give you some equations for the deflection. The deflection is going to be this symbol right here. It is a lowercase Greek delta, and the maximum deflection is in the middle. This is the point of maximum deflection. So we'll note that with the subscript max. So delta max is the maximum deflection in the beam. It's this right here. It's this distance right here. What we'll talk about in this slide presentation are the 4 different factors that I've already mentioned in the virtual experiment. These 4 different factors that affect the amount of deflection in a beam, or you could also think about it as the amount of force that the beam can support. They're kind of 2 different ways of thinking about the same idea. To do that, we're going to calculate the moment of inertia. That's one of the big calculations that we're going to get to today. And we're going to talk about some equations for the maximum deflection in a beam. One thing that we'll talk about is called the flexural modulus. You can think about this as being pretty similar to the elastic modulus for tensile testing or compressive modulus for compression testing. Now we're doing beam bending testing, which is flexural testing. And so it's natural that we have a different kind of modulus, which we're going to call the flexural modulus. And we'll have 4 different equations for the stress in the beam, the maximum stress in the beam as it's being tested. And we'll talk about these terms, the flexural yield strength, which you can probably guess what that's going to signify, and the flexural strength. You can probably make a pretty good guess about what that's going to mean also. All right, here's the answer to that question that I gave you just a minute ago. As we're bending a beam, as it's being bent, is it in tension or is it in compression? The answer is both. As we're applying a force to the beam and we're trying to bend it, the upper surface of the beam that's up here is actually in compression. We're trying to squish the fibers together. And the bottom surface of the beam is actually in tension as we're pulling the fibers apart. I was thinking about a wooden beam, but you can think about grains in a metal beam if you want to. In any kind of beam, as we're applying a bending load, you're always going to have compression on the upper surface and tension in the lower surface. This area right here where there actually is no stress is in the middle of the beam, and we call that the neutral axis. The way that beams are almost always going to fail, I won't say always, but almost always, they're going to fail due to the rupture of the outer fibers in this material that's in tension. Why is that? Because most materials are weaker in tensile stress than they are in compressive stress. Most materials are worse in tension than they are in compression. And so therefore, the failure is going to occur where you have the maximum tensile stress, which is way out here on the edge of the beam, on the bottom side of the beam, and then progressively that failure is going to rupture up through the beam, starting at the outside edge and then coming up towards the neutral axis. The amount of bending that you're going to get, we talked about these 4 things just a few minutes ago. It depends on the material itself. How stiff is the material? That's a material property. It also depends on the geometry of the beam, not just the cross-sectional area, but also the shape of the beam. Like this was the 2x4 that was horizontal versus the 2x4 that was vertical. That affects something called the moment of inertia that we'll talk about in a few minutes. The third one is how the beam is supported. Is it a cantilever? Is it a simply supported beam, or is it fixed on the edges? So how do you support the beam? And the last one is how do you apply the load to the beam? The 2 extremes that we'll talk about are a point load or an evenly distributed load across the span of the beam. So as you're thinking about these, note that these first 2 have to do with the beam itself. Like what is the shape of the beam and what's the beam made out of? The third one has to do with how you support the beam. And the fourth one has to do with how you apply the load to the beam. All of those things affect how much load the beam can support. We'll talk a little bit more about each one of these, but we'll go through these briefly at first. So first of all, the first thing we'll talk about is the material property, the material stiffness. And the material stiffness is given by a material property called the flexural modulus. And we abbreviate that E sub B. The little b down here stands for bending. So we had E before, that was the elastic modulus, either in tensile testing or compression testing. And now we have another type of modulus, and that is the flexural modulus. Normally, the flexural modulus is something that you're going to look up in a table. So you might go to matweb.com and you'll look up the flexural modulus for oak or maple or pine or whatever you build your beam out of in Lab 8, whatever kind of wood you decide to build your beam out of. And we have a bunch of different kinds of wood in the Woods lab where you're going to build your beam. So you're probably going to look up the flexural modulus for whatever type of wood or woods you select to build your beam out of in Lab 8. The next thing is the geometry of the beam, not just the cross-sectional area, but actually the way the beam is arranged horizontally or vertically, or an I-beam or some other type of beam. And you know this changes something about the degree to which you can bend a beam, right? You know that experimentally, and you saw from in the lab just a few minutes ago that it changes how much weight it can support. If I had that little 1x2 that was horizontal, it could not support my body weight. But if I had it vertical, it could barely support my body weight, but it could support my body weight. If you had something larger like an I-beam, then if it was a large enough I-beam, then it could easily support my body weight and much more. So we'll talk about how to calculate the moment of inertia in a few minutes, which is what the beam geometry really depends on, the moment of inertia of this beam. The end conditions that we'll talk about, there's 3 that we're going to talk about in this class, and the 3 that we'll talk about are simply supported, where the beam is just resting on this support and on this support. But the key thing about the simply supported beam is that these supports cannot apply a torque to the beam, all right? The beam is just resting on those supports, and the supports don't apply any kind of a twisting or a torque to the beam. The next one we'll talk about is cantilever. The cantilever beam is fixed on one end and free on the other end. And the last one is fixed at both ends. And this is the situation that I talked about before, where if I actually fixed and clamped the beam to both supports, now this support actually could apply a twisting force, a torque, to the beam on this edge, or this support could apply a torque to this beam on this edge. We're actually not going to talk in very much detail about this last situation in this class. The 2 cases that we're going to focus on in this class, because they're most common, are these upper 2 cases, the simply supported beam and the cantilever beam. The last of the 4 things that affect how much load your beam can support are the loading conditions. Of course, there are a virtually infinite range of loading conditions, so we're going to simplify it and talk about 2 in this course. One case is a point load, where all of your force is applied at one point. For the case of a simply supported beam, the force is applied in the middle. Or if we were talking about a cantilever beam, we'd say all of the force is applied at the tip of the cantilever beam. So that's going to be our point load application. Or the other way is a distributed load. And we're going to talk about a uniform, that means evenly distributed load. So this is like a bookshelf. Picture a bookshelf like up here. And imagine that these were all the same book. So it's a totally uniform load across the length of the shelf. Then we'd have a certain number of pounds force per foot that would be applied as the load on this beam. Next, we're going to talk in a little bit more detail about each one of those 4 different parameters that affect beam bending. And the first one is the material stiffness. And the material stiffness parameter we call the flexural modulus. The flexural modulus is the parameter that you look up, and it's analogous to the elastic modulus in tension or the compressive modulus in compression. The most critical part of the beam is usually the outside lower edge right here. Like I mentioned before, that's where the failure almost always starts in a beam bending test. Why? Because most materials are weaker in tension than they are in compression, and the maximum tensile stress is right here on the bottom of the beam. So you have the maximum tensile stress here, and then gradually, as you go up, the stress gets lower to the point where the neutral axis has no stress. So That's why the failure starts here on the bottom of the beam. All right, I think I've said most of this. The material property that we're interested in is the flexural modulus E sub B. The units for that are PSI, just like the modulus in tensile testing and in compression testing. And you can think about this as the material's resistance to bending. Just like the elastic modulus was the material's resistance to tensile stretch, and the compressive modulus was the resistance to compression. And so if you think about that, you might think that, all right, the most critical part of the beam is the lower edge, and the lower edge is in tension. So you might think that the flexural modulus, well, it should be the same thing as the Young's modulus or the elastic modulus in tension, right? And that's a good line of thinking, if you're thinking that. That is on the right track, but it's not quite true. They're not identical. And the reason they're not identical is because in beam bending, that place on the lower edge where it has a maximum tensile stress is actually reinforced by the material directly above it, which has a lower stress. And that material is reinforced by the material above it, which has a lower stress yet. So as a result, they're similar, but they're not going to be identical. The flexural modulus is not going to be identical to the elastic modulus in tension. All right, so they're similar. I think I've said most of this. So the material on the bottom edge is actually reinforced by the material above it, which has a lower stress value. And for the part to completely fail, then all of that, the whole part, has to fail. So usually what you find is that the flexural modulus is usually somewhere around 1 to 1.5 times the elastic modulus value. So if you are looking up the flexural modulus on matweb.com or some other resource, if you can't find the flexural modulus, because not every parameter is always given for every material, you can make an educated guess, and you can say that, okay, I can't find the flexural modulus, but I can find the elastic modulus for tensile testing. So you can make a guess that the flexural modulus is maybe 1.25 times the elastic modulus in tension. That would be a pretty reasonable guess. So flexural modulus has to do with the material. It's the material property that is the resistance to bending. The next thing we'll talk about is the geometry of the beam. So from the experiment and from playing around in the past, I'm sure that you know that as you change a 2x4 from laying on its horizontal, longer flat side to on edge, then it's different. It gives you a different amount of bending. Similarly, if you took a 2x4 and you replaced it with a 2x6 or a 2x12, which is what the majority of floor joists are, floor support beams are in houses, you'd see that there's a lot less bending for a 2x6 than a 2x4, or for a 2x12 than a 2x6. And that all comes down to a quantity or variable known as the moment of inertia. And the moment of inertia, for some convention, for some reason, the convention is to call the moment of inertia I. That is the variable or symbol that represents the moment of inertia. One analogy that I like to make for me when I'm thinking about beam bending, it's not a perfect analogy, but I think it's helpful, is the idea of torque. Remember, torque is a twisting force. So if you're talking about the torque on a bolt and you're tightening it with a wrench, then the torque on that bolt is the length of the wrench times the force that you're applying, the force times the distance. Now, when we're applying this to beam bending, let's suppose we have a point load that is applied to a simply supported beam, and we have talked about how the most critical point on that beam is the lower edge that's in tension, right? So those fibers or those grains that are on the bottom edge of that beam are trying to hold the beam together. They're trying to hold the beam together and prevent it from failing. That's what those fibers or grains on the bottom side of the beam are trying to do. The effectiveness with which those grains or those fibers, if it's wood, that are trying to hold the beam together, the effectiveness that they can use to hold it together is equal to, well, number one, how much tensile load can those fibers or grains support? So that's like how much force can they apply to keep the beam in one piece. But also the lever arm that those fibers have to use is the distance between the bottom edge of the beam and the neutral axis of the beam. So they do actually have some leverage, and that leverage is the distance between the bottom edge of the beam and the neutral axis of the beam. All right, so if you're trying to make a beam that doesn't bend very much, so a strong beam, then you'd want to maximize the amount of force that the material can provide. So we'll talk about that a little bit later, but you want to pick a material with a high flexural yield stress. That is to say, a strong material in flexural testing. So you pick a strong material, but also what we're talking about now is the shape. So also you want to maximize the distance of that lever arm. So you want to maximize the distance between that bottom edge where those fibers are trying to hold the material together. You're going to maximize that distance between the bottom edge and the neutral axis of the part, because that acts like a lever arm that those fibers or grains can use to keep the beam from breaking and failing due to beam bending. All right, and this second part is related to the moment of inertia. So this is starting to explain why a beam is stronger, or why a 2x4 is stronger on its edge as opposed to horizontally. So if we maximize the distance from the neutral axis to the bottom of the beam, that is going to maximize something called the moment of inertia of the beam. And I'm going to give you a formula to calculate the moment of inertia in just a second. And what the moment of inertia is, it's the resistance to deflection due to the geometric shape of the part. Here are the equations for the moments of inertia. And these are really all you're going to need for this class. These are the only two equations that you're going to need for moment of inertia. This is the equation for moment of inertia for a rectangular shaped beam. No matter if it's tall and skinny or flat and wide, it doesn't matter. You can use this formula. Any type of rectangular or prismatic type shape, you can use this formula. And any type of round shape, you can use this formula. All right. As far as the units, think about what the units are going to be. We're going to have the base, that's this dimension. You can think of it as the width if you want, times the height cubed. The height is this dimension right here. So it's probably most common to talk about this in terms of inches. So let's say the base is in inches and the height is in inches. So for units here, we're going to have inches times inches cubed, which is going to give us inches to the fourth. So the units for a moment of inertia is going to be inches to the fourth power. Likewise down here, it's easier to see down here. Pi is a constant. The radius we can measure in inches. So inches to the fourth power gives us units of inches to the fourth. All right, so this might seem too simple. Like, how are we going to calculate the moment of inertia for pipes or for I-beams? But it turns out you can, and it's not that difficult. What you do is you take the moment of inertia for the solid shape, and then you subtract what the moment of inertia would be for the hollow section inside there. So if you have a pipe of outer radius big R and inner radius little r, then what you do is to calculate the moment of inertia for this pipe, you calculate the moment of inertia for a solid cylinder with radius big R, and then subtract the moment of inertia for a cylinder with radius little r. So what you're really doing is you're just subtracting the moment of inertia for this hollow section inside here. All right, so it's actually pretty simple. Same thing for an I-beam. Let's say we want to calculate the moment of inertia for this I-beam. What you do is you calculate the moment of inertia for this full rectangle, and then you subtract the moment of inertia for these hollow sections right here. So you calculate this moment of inertia for the whole part, then you calculate the moment of inertia for this section right here, and you subtract the moment of inertia for this section as well as for this section right there. And after you do that, that gives you the moment of inertia for the I-beam itself. You may have noticed before that a lot of buildings and structures are made from I-beams, not usually solid, prismatic, rectangular pieces of steel. And now, by understanding moment of inertia, we can explain why that is. The reason is because the parts of the structure that are near the neutral axis don't contribute very much to the moment of inertia. Why? Because we have the height cubed. So it's the parts of the beam that are far away from the neutral axis on the top and the bottom that contribute significantly to the moment of inertia. The parts of the beam that are really close to the neutral axis don't really count for much because it's the height cubed. And those parts of the beam, if they're close to the neutral axis, that height h value is really small. So it doesn't really count towards the moment of inertia very much. So what we try to do is we try to put as much material as possible far away from the neutral axis of the beam, and that increases the moment of inertia because we have the height cubed, and that makes a big difference when you have an exponent like that. Let's apply this concept of moment of inertia by thinking about this piece of sheet metal that is 0.1 inches thick, and let's say we want to double the rigidity of this plate. So this is like a piece of sheet metal, you know, and you can take it in your hands and you can wiggle it and it goes wah, 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 right? You ever done that with a piece of sheet metal? It makes that funny sound. So we want to make that more rigid so that it's not as easy to wiggle like back and forth like that. So one way of changing the rigidity is to change the material that you're making this out of. But let's say we didn't want to do that. Let's say we wanted to keep the same material. We just want the parts to be more rigid. All right, we want to double the rigidity of this plate. All right, so we know the formula for moment of inertia, and we know that the height term in the moment of inertia is a cubic function. So if you play around with the numbers a little bit, it turns out that if you take 1.25 cubed, you get about 2. So if you make something like this plate about 25% thicker, then you'll actually get a specimen that is about twice as rigid, not due to the material that you're making it out of, just due to the shape of the part that you're using. So you could, one way of doing this, you could make the part 25% thicker. All right, that is one solution to this problem. You make this specimen 25% thicker, and now it's about 0.125 or so inches, a little bit of rounding error, but about 0.125 inches. And now you've got a part that is twice as rigid as this part right here. But the problem with doing that is that if you have made the part 25% thicker, then you've also increased the mass of the part and maybe the cost of the part by 25% as well. So there might be a better way of doing that. So if you want to make this plate twice as rigid, there is an alternative to making it 25% thicker. You can also add a center rib like is shown right here. And you can do the math and you can figure out what would increase the rigidity by a factor of 2. But as an example here, if you made this rib 0.05 inches wide, then you could make it 0.116 inches tall, and that would also increase the rigidity of this plate by a factor of 2. There are lots of examples of people doing this, of taking, a piece of sheet metal or paper or something and changing the shape and the geometry of the plate, increasing the moment of inertia and thus making the part a lot more rigid so that it won't deflect as much. So all of these different options are ways that you can increase the moment of inertia for a specimen that originally was pretty flat and maybe kind of wobbly and flimsy. Here are some more examples. This is just paper that is turned into cardboard by adding a section in the middle that increases the moment of inertia. Also, this is just sheet metal that's been turned into metal roofing by adding some ridges, thereby increasing the moment of inertia of the sheet metal. This is like a honeycomb structure. The whole point of this section in the middle is not to add strength through the strength of the honeycomb, but just to separate these layers of, say, this could be carbon fiber or fiberglass. And so when you put these materials together, then you get a much stronger specimen because you've separated the upper and lower surfaces, thus increasing the moment of inertia of the part. Here too, this applies to pipes. You got like a culvert pipe here and a drainage tile up here. And because you have corrugations in the part, you've increased the moment of inertia. And now you can drive a tractor over these things. You know, these are often put in ditches, and you put them in and put some dirt over it, and you're going to drive a tractor or a combine over it that weigh, you know, many, many tons. So while sheet metal itself is not particularly rigid, if you put these corrugations in it, you increase the moment of inertia, and now you've made it into a very rigid part. So we've talked about flexural modulus. That gives you the material's stiffness, the inherent stiffness of the material in a bending situation. And we've also talked about the moment of inertia, which is the geometric stiffness, how you can change the shape of the part to make it more stiff in a bending situation. If you multiply those two together, E sub B times I, then you get what you call the flexural rigidity, and that's the overall rigidity of the specimen due to both the material that it's made out of as well as the shape of the specimen. So you should know all of those terms. You should know flexural modulus, you should know the moment of inertia, and you should know flexural rigidity. And you should know that flexural rigidity is equal to the product of flexural modulus and moment of inertia. I think that's a good place to end this video to break this material up. So if you recall, in this video, we talked about 4 different things that affect the amount of bending load that a beam can support. And in this video, we talked a little bit more in detail about 2 of those. We talked in more detail about the flexural modulus, and we talked about the moment of inertia, and we talked about how the product of those 2 gives you something called the flexural rigidity. In the next video, we're going to talk about the remaining 2 things that are relevant for beam bending. That is the way the beam is supported and the way that you apply the load. And then from there, we can get our calculations. So I'll give you some formulas for stress in a beam, and I'll give you an equation, a couple of equations for deflection in a beam. How much does the beam deflect when you apply a load to it? All right, so that's going to wrap up this video. I'll see you in the next video.